So for this part, I promised you to talk about data authenticity in a little bit more detail. And there's a lot of words on the slide, so I hope you can see from the far away. But what essentially we're trying to highlight kind of in NDN, besides that everything is named pieces of data. So the data itself is named piece of data. The key that is needed to verify authenticity of piece of data is also piece of data. It has a name, and kind of so on and on and on. And the important observation is not all keys kind of equal. Like not all keys can sign specific piece of data or can be used to verify the specific piece of data. And we have to have a mechanism to actually restrict that this specific key can only sign that specific sets of data. This is kind of in some relationship to today's HTTPS, where the kind of PKI certificate that you got from whatever certificate authority only authorizes you to kind of create the website on a specific name. But with NDN, we're going way farther in this direction, making this decision not based on a kind of connection to the website, but rather per data packet itself. That's the first element that we're going further. And the second one is the relationship between key name and data name can be a little bit more complex than just basically URL or something else. As Tamer mentioned before, there's a set of data that exist in a system or being produced as part of the application process. So, for example, there's the actual chat messages, the synchronization messages that Alana was talking about, and some other things. So all of those data should be kind of effectively signed by some key. And for example, kind of this is extremely simplified version because in reality we have to have multiple keys that will sign different pieces of data for the purpose of the least privilege principle. But given this as a simple example, all those data has to be signed by this specific key, by the app's Mike key. So only Mike can sign data that's been produced by Mike. So that's kind of obvious restriction. But as I can show in one of the next slides, this is not exactly prefix. So there is some relationship to Mike, there is some relationship to the application key, but it's not always exactly the same kind of prefix match. And if I go kind of what I'm trying to highlight, so I mentioned it's not exactly the prefix, but we need the kind of reasonable mechanism to actually express all those relationships. Like we cannot really expect application developers to kind of imagine a way to match all those prefixes together. So for that purpose, we actually invented the concept, kind of it's a simple thing, but the concept of a trust schema. And the trust schema is effectively a mechanism, a formal mechanism to define this relationship, like what kind of data is, what data name, and what key is authorized to sign this data. And instead of just going by kind of enumerating all possible names, possible names of the keys, we defined the kind of simplified language that based heavily on regular expressions. And you can see what exactly happening here. So if you kind of go for the, let's say, chat messages, so there's a kind of a naming that would match the messages of the data being produced that have some prefix, some identification of the user, identification of the kind of application, a group that this chat message belongs, and some other information. And this chat message have to be signed specifically by the user's key. And as you can point out here, the two things from that data name have to be present in the user's key. So for example, user has to be there and the prefix has to be there. As you can see here, it's not, again, group is not part of this picture, but it also can be part of this trust schema if it's designed in a bit more complex way. But as you can see, like only this specific user will be able to sign that specific pieces of data. That's not always the case. So, for example, in the case of sync data, we allow in all users who participate in a group to sign the messages. So, effectively, there is no indication of the user. So, there is actually a small error in here. So that's kind of a very, very high-level introduction to the trust schema. Just to highlight, there's a kind of a lot of power of names. Like I talked quite a bit about the use of names for enabling access control. This is another part of use of names to build the verification, like meaningful verification of data using kind of rule matching between the data and the key names. And one interesting part for kind of defining trust schema in this specific way is to make sure that, again, application developers don't design a trust schema don't have to design a trust schema every time they develop a kind of similar application. So in this case, the top part of this application is purely generic. It can be deployed in kind of different environments, assuming somebody deploys different trust anchor. So this is kind of the trust anchor is what ties the whole security of the whole system together. So if we use the application key, like in this case, or apps key or version 5, that would be one environment. If it's potentially some different mission or some different notional environment, we can have a different trust anchor that would absolutely work with existing trust schema, but in completely different environment. And to highlight a little bit more of naming convention, I'm not going to go into detail of the access name-based access control for the chat application, given most of the parts is very, very similar to what I have been talking in a previous talk. But one thing that I wanted to highlight is kind of extensibility of the policies, or like ability to control granularity of the access by, again, adding additional parts of the name. So in the previous talk, we only talked about NAC for global, or the PLI global. So in here, the access control can be defined for different kind of chat rooms effectively, and this control will be defined completely separately for different chat rooms. And that would be responsibility of the guy who created the chat room effectively to define whom he wants to invite in this chat room. But the rest of the process is exactly the same thing. So the guy defines the policy by creating the corresponding key encryption key, key decryption key. He invites or giving access to the chat room by kind of encrypting key decryption key to using the public keys of all participants he wants to get access to, and everybody can publish data in this chat room using whatever symmetric key cryptography. Okay, that's kind of to summarize. NDN give a lot of bring a lot of security properties to network communication. So you can always, primarily we talked before about the protecting data packet, but you can also have the additional signature or protection, or even some part of the encrypting part of the name of the interest packet. You effectively, by doing all this signing of the packets and encrypting packets, you mitigate the problem of injection of the packets, because you can always verify authenticity of the data. So again, like my objective, like in all this talk about the security, is to highlight the power of names to be used as part of the kind of applying security in this environment. If names are designed, like if you put like meaningful information in the names, you potentially open some abuse of that. Ideally, you want to kind of remove some of the information that you can extract from the names. There are different approaches. So one of the approaches that was published in ACM 2017 conference was to kind of do encapsulation approach. It works. There's always some kind of trade-offs in the approaches. There was a different approach proposed a couple of years back called Andana, effectively trying to make some form of a Tor-like system where kind of you hide the name and then hide the name. But again, in all of those cases, you kind of potentially losing some of the capabilities that this expressiveness of the name provides.